In the last lecture, we saw that the homogeneous system plays an important role, one, in deciding the uniqueness of the solution of the non-homogeneous system, and finding all solutions of non-homogeneous system, knowing one particular solution of the non-homogeneous system. We said that the main tool for this are the elementary row operations, the so called elementary row operations, which we said we will denote by ERO for short. There were three types of EROs which we introduced. So, we shall discuss this one by one. The first type, ERO of type 1. This is called row exchange. What does this do? Keeps all but two rows unaltered, then interchanges the position of these two rows. For example, if we interchange ith row and jth row positions, we shall denote this by R I J. R stands for row and I and J are exchanging positions. For example, if we take the matrix A 0, 1, 2, 3, 2, 1, then when we put the arrow and write R 1 2, what we mean is we are applying an elementary row operation on the matrix A. The operation is row exchange, and this is 1 and 2, say the first and the second row are going to be interchanged, and this results in 3 2 1 0 1 2. The resulting matrix will denote by A 1. So, in general, if we have a matrix A belonging to F m cross n and we apply the ith row jth row interchange on that, and what results is the matrix A 1. This is what is known as the elementary row operation of type 1. Some simple properties we will observe. Some simple properties of ERO of type 1. Clearly, in this example, if we again interchange the first and the second row, we will get back to the original matrix. In other words, the interchange is a reversible process or an invertible process. So, the first property we observe is that the ERO of type 1 is invertible. And if we have the transformation or the row operation as Rij, its inverse is again Rij. If you want to annul the exchange of the ith and the jth row, you have to again exchange the ith and the jth row, so that they get back into the original position. So, the ERO of type 1 is invertible, and the inverse is also an ERO of type 1. So, the inverse of an ERO of type 1 is an ERO of type 1. So, if we have A going to A1 under the ERO of type 1 of exchange of the ith and the jth row, and then A1 will go to A again by an interchange of the ith and the jth row. So, this is the first observation we make. Now, the second one, we will first look at the example we had. We had 0, 1, 2, 3, 2, 1 was our matrix, and we applied R12 to it, and what we got was 3, 2, 1 and 0, 1, 2. This we called as A1. Now, let us look at the homogeneous system. Look at the homogeneous system corresponding to A, the original matrix, and A1, the matrix that has been obtained from A by applying an ERO of type 1. So, Ax equal to, now M, this is 2 by 3 matrix. So, M is 2. So, Ax equal to theta 2 corresponds to x2 plus 2x3 is equal to 0, 3x1 plus 2x2 plus x3 equal to 0. The homogeneous system corresponding to A1 is 3x1 plus 2x2 plus x3 equal to 0, x2 plus 2x3 equal to 0. We observe that both are the same systems, the same equations appear in these systems, only the order in which we write these equations are different. So, both systems are same, only the order of the equations is changed. What does this imply? This implies that whenever something is a solution for the system Ax equal to theta 2, it will also be a solution for the system A1 equal to theta 2 and vice versa. So, the conclusion we can draw is that the homogeneous systems Ax equal to theta m, theta 2 and A1x equal to theta 2 have the same set of solutions, the same set of solutions. Now, it is easily seen that the same thing happens in the general situation of an m by n matrix, because all equations except 2 are put in the same position and 2 equations are interchanged in their positions, and therefore, both of them will have the same set of equations. So, in general, if A is an m by n matrix and we get A1 from A by an elementary row operation of type 1, then the homogeneous system Ax equal to theta m and A1x equal to theta m have the same set of solutions, the same set of solutions. and therefore, we can solve the system A x equal to theta m or the system A 1 x equal to theta m. This is the second simple property of the elementary row operation of type 1. What it says is, by applying the elementary row operation on the matrix A, you are not destroying the set of solutions, you are not removing any solution, you are not creating any new solution, the same set of solutions remain for the resultant matrix also. The third observation we will make is, let us get back to our example. We had A equal to 0, 1, 2, 3, 2, 1, which is a 2 by 3 matrix, and when we applied R 1 2, we got 3 2 1 and 0 1 2, we call this matrix A 1. Now, let us look at the value of m in this case, it is 2. So, we look at the 2 by 2 identity matrix, which is this, and we apply the same elementary row operation which we applied to A to this matrix, and we get this matrix 0 1 1 0, which we will call as E. Now, look at E times A, that is pre-multiply the matrix A by E, which is 0 1 1 0 times 0 1 2 3 2 1. When we carry out the multiplication, we get this, which is precisely A 1. In other words, the effect of operating with ERO type 1 on A is the same as pre-multiplying the matrix A by E, where E is obtained by effecting the same transformation on the 2 by 2 matrix. So, pre-multiplication by E, pre-multiplication of A by E produced the same effect as the ERO. Now, this is now we can see that this is in general true. So, the conclusion is, if we have an m by n matrix analogously in the general situation, and if A 1 is obtained from A by R A j, then look at I m, the m by m identity matrix, apply R I j, the same elementary row operation that we did on A, to the identity matrix I m to get a matrix E, then E A will be equal to E 1. So, pre-multiplication of this type of matrix effects the same change as applying the elementary row operation. So, this is the first type of elementary row operation that we consider. The second type of elementary row operation here, what we do is keep all rows except one row unchanged. We keep all rows except one row unchanged. Then let us say all rows except jth row are kept unchanged. Then we are going to effect a change only in the ith row. To the ith row, I am sorry, to the jth row, add alpha times the ith row. We write this as R j, to the jth row we are going to add alpha times the ith row. So, we take a matrix A and we apply this transformation. The jth row is replaced by the jth row plus alpha times the ith row to get a new matrix. This is the elementary row operation of type 2, and the notation we use is R j plus alpha R I. Let us look at an example. Let us say A is equal to 1, 2, 3, 1, 0, 1, 0, 1, 2. This is our matrix. Now, it is a square matrix, it is irrelevant, any square or rectangular matrix we can perform this. So, now let us look at the transformation when we write R 3 plus 2 R 1. What we mean here is, it is the third row alone that is undergoing a change, because R 3 plus, so R 3 is going to change, R 1 and R 2 are going to be the same. So, R 1 and R 2 are unaltered and R 3 is going to change. And how is it going to change? To the third row we are going to add twice the first row. So, we get 3 plus 2 5, 1 plus 2 3 and 2 plus 0 2, and this matrix we call as A1. So, here is an example of elementary row operation of type 2. In general, we denote it by R j plus alpha times R I if the jth row undergoes the change by adding alpha times the ith row to that. Alpha can be any number in F. It can be positive, or if F is real, alpha can be positive or negative or 0. If F is complex, it can be positive, negative, real, or it could be pure imaginary, or it could be any complex number. Now, let us look at simple properties of ERO of type 2. Once again, we observe that if we change the jth row by adding alpha times the ith row, to annul this change, to get back to the original position, we have to remove whatever we had added. So, we have to subtract alpha times the ith row. So, we have that the first property, that ERO of type 2 is invertible. That is, if we have R j plus alpha R I, to reverse that process, from the jth row whatever was added must be removed now. So, it should be minus alpha times R I. For example, in the above example we had 1 1 0, 2 0 1, 3 1 2, and this was the matrix A, and we had R 3 plus 2 R 1, and we got 1 1 0, 2 0 1, 5 3 2. Now, to annul this, if we do R 3 minus 2 R 1, we will get back to A. This is what we mean by saying that the ERO of type 2 is invertible. Notice that the inverse R j plus minus alpha times R or I is also an elementary operation of the type 2, because again we are adding a multiple of some row to another row. So, the inverse of an ERO of type 2 is again an ERO of type 2. That is the first fundamental property of EROs of type 2. Let us look at previously when we discussed with ERO of type 1, we have found that it was invertible and inverse of ERO of type 1. Again we have found that when you deal with ERO of type 2, it is invertible and the inverse is again ERO of type 2. And when we discussed ERO of type 1, we said that it does not alter the solutions of the homogeneous system. Thus, we would like to know whether the same thing is true here also. Let us again look at our example. We had 1 1 0, 2 0 1, 3 1 2. This was the matrix A, and we did R3 plus 2 R1 to get 5 3 2, which is A1. Now, look at the homogeneous systems corresponding to A and A1. So, we have Ax equal to theta 3, now m is 3 in this case. The equations are x1 plus x2 equal to 0, 2x1 plus x3 equal to 0, 3x1 plus x2 plus 2x3 equal to 0. The system corresponding to A1 is x1 plus x2 equal to 0, 2x1 plus x3 equal to 0, 5x1 plus 3x2 plus 2x3 equal to 0. Now, we see that if any x1, x2, x3 satisfies this set of equations, it will certainly satisfy the first equation in the A1x because they are same. It will certainly satisfy the second equation in A1x because they are the same. It will also satisfy the third equation because the third equation is nothing but the third equation of the first set plus twice the first equation of the first set, and since the first equation is satisfied, they will also be satisfied. Similarly, in the reverse manner. So, what we observe is that the two homogeneous systems Ax equal to theta 3 and A1x equal to theta 3 have the same set of solutions. Therefore, whether we solve Ax equal to theta 3 or A1x equal to theta m. So, in general, analogously for any m by n matrix, we see that this is true. So, in general, if A is an m by n matrix and A goes to A1 under the transformation Rj plus alpha Ri, then the homogeneous systems Ax equal to theta m and A1x equal to theta m have the same set of solutions. Therefore, whether we solve the system Ax equal to theta m or whether we solve the system A1 equal to theta m, both are equivalent because we are going to get the same set of solutions. The third, again when we look at ERO of type 1, we found that the ERO of type 1 can be implemented or effected by pre-multiplying the matrix by a new matrix obtained by applying the same transformation to the identity matrix. let us look whether that is true in this case. Again let us look at the example we had. We had A equal to 1 1 0, 2 0 1, 3 1 2. We did the operation R 1 R 3 plus 2 R 1 to get a new matrix 1 1 0, 2 0 1, 5 3 2, which we called as A 1. Now, we have a 3 by 3 matrix, M is 3 in this case. So, we consider the 3 by 3 identity matrix, and now on this we apply the same transformation we applied as above, R 3 plus 2 R 1. What do we get? I is 1 0 0 0 1 0 0 0 1. So, when I apply this transformation, I get 1 0 0 0 1 0. The first two rows are not affected. The third row is going to change by adding twice the first row to it. So, we get this. This is what I call as E. So, when I apply on I this transformation, now easy to verify. When we pre-multiply E and A, what we get is precisely A 1. So, thus we see that the ERO of type 2 can be effected by a pre-multiplication EA, where if the ERO of type 2 is Rj plus alpha Ri, E is obtained from Im by applying Rj plus alpha R. Thus, in all the three cases, if we summarize, we see the following. We had three types of EROs. Type 1, which we simply denoted by Rij, interchange of ith row and jth row. Type 2, Rj plus alpha Ri. Now, what is the third type? What are the two these two fellows possess in common? The common thing is they are invertible, inverse is again same type ERO, the effect can be achieved by pre-multiplying. We will simply write by an E. We understand what we mean by an E. The E means on the identity matrix apply the same type of ERO. The third type we will introduce is again going to possess the same properties. It will also be invertible. They do not change the solutions of homogeneous system. The third type also is going to possess the same properties. It is again a simple ERO, again all but one row remain unaltered, all but one row remain unaltered, only one row undergoes a change, say the except the ith row, all remain unaltered except the ith row. What do we do on the ith row? It is the ith row that is going to undergo a change. what the type of change that we will make is, we are going to multiply every entry in the ith row by a number alpha in F, where alpha is not 0. So, we are going to multiply every entry in the ith row by a non-zero number. This is a very important operation. Later we will see it brings in some normalizations in the reductions that we do. For example, let us take the matrix 1 0 minus 1 2 1 2. Let us say we are going to change the second row. What is the change we are going to make? We are going to multiply every entry by minus 3. So, what do we get? 1 0 minus 1 minus 6 minus 3 minus 6. We call this matrix as A1. So, again we look at some. So, in general, okay, let us fix the notation. In general, alpha r I would mean we are multiplying ith row by alpha, where of course alpha will be non-zero. So, again we observe some simple properties of the elementary row operation of type 3. Now, look at the above example. Look at the systems homogeneous systems, Ax equal to theta, in this case m is 2, n is 3. So, we have to take theta m, which is theta 2, and A1x equal to theta 2. What are these two systems? The equations here are x1 minus x3 equal to 0, 2x1 plus x2 plus 2x3 equal to 0. The equations here are x1 minus x3 equal to 0, minus 6x1 minus 3x2 minus 6x3 equal to 0. Now, look at these two systems. The first equations are the same, and therefore, whichever satisfies the first equation on this side will also satisfy the first equation on that side, and if anyone x1, x2, x3 satisfy the second equation on this side, it will also satisfy the second equation on that side, because it is just both sides multiplied by minus 3. Similarly, if anybody satisfies the second equation on the right side, it will also satisfy the second equation on the first side, because it is only division by minus 3. That is why we wanted to assume alpha not equal to 0, because we want to divide by alpha. So, both have same set of solutions. Thus, so in general, if I have a matrix which is m by n, and I go from A to A1 by multiplying the ith row by alpha I, alpha not equal to 0, then the homogeneous systems Ax equal to theta m and A1x equal to theta m both have the same set of solutions. The second property that we observe about the ERO of type 3 is that, just like the other two EROs, this is also invertible. ERO of type 3 is invertible, because if we obtain A 1 from A by multiplying all the entries in a particular row by a non-zero constant, we can annul this effect by multiplying by the inverse of that non-zero constant, the same row. So, therefore, we have, if alpha R I is the row operation type 3, then its inverse will be multiply the ith row by alpha inverse. And now, this alpha inverse makes sense because we have assumed alpha not equal to 0. That is why it is important to state in the elementary row operation type 3 that it is multiplication of a row by a non-zero alpha in F. So, the ERO of type 3 is again an ERO of type 3 because it is again multiplying the ith row by some number. So, this is again an ERO of type 3. So, therefore, if we have A and we get A 1 by alpha R I, then we will get back to A from this by alpha minus 1 R I, alpha to the power of minus 1 R I. The third important property, let us look at our example. A was 1 0 minus 1 2 1 2 and we applied minus 3 times R 2 to get minus 6 minus 3 minus 6, which we called as A 1. Again, as before, observe this is a 2 by 3 matrix, therefore, M is 2 in this case. So, we consider the identity matrix 2 by 2, which is 1 0 0 1. Suppose we apply the same transformation on this, we get 1 0 0 minus 3, which we will call as E. If we now multiply E and A, what we are going to get is that 1 0 0 minus 3 into 1 0 minus 1 2 1 2, which is just 1 0 minus 1 minus 6 minus 3 minus 6, which is A 1. So, once again the ERO of type 3 can be implemented or effected by pre-multiplying A by an E. We know what is meant by an E. Take the identity matrix and apply the same transformation to the identity matrix. So, thus in all the 3 cases of these elementary row operations, the 3 fundamental properties that we observe are, so all EROs have the following properties. 1, they are invertible. Inverse is of the same type. 2, they do not alter the solutions of the homogeneous system, and 3, they can be effected by pre-multiplication by an E, pre-multiplication of A by an E. We again we tacitly understand what we mean by E. So, now what we will do is, let us take Fmn and let us denote by E to be the set of all elementary row operations on m by n matrices. All possible elementary row operations on m by n matrices. They may be of type 1, they may choose any arbitrarily 2 rows and exchange them, or add a multiple of some row to another row, or multiply some row by a non-zero constant. So, take all possible elementary row operations on m by n matrices and call them as E. This is the collection of all elementary operations on m by n matrices. Now, suppose I take I m, the m by m identity matrix, and take E in E, that means E is an elementary row operation, and I apply E to this, I am going to get, let us call it as E naught, and then we get a matrix E. That is, by applying an elementary operation, an identity matrix, we get a matrix E. Such matrices are called elementary matrices. So, therefore, an m by m elementary matrix is a matrix obtained by applying an elementary row operation, any one of the elementary row operations from this collection on I m. So, therefore, what we had observed was that EROs are effected by pre-multiplying A by an element by elementary matrices. That is the important observation to make. Any type of ERO can be effected by pre-multiplying the given matrix by a suitable elementary matrix. Now, let us look at FMN. Take two matrices in FMN. So, I am looking at two matrices of the same size, and suppose there are elementary row operations, let us call them as E1, E2, some Ek, that is, these are all in the collection of elementary row operations. Each one is an elementary row operation. Suppose they are such that when I apply on E, successively the elementary row operations, I get A1, then I apply the elementary row operation, I get A2, and so on and so forth, and finally I apply the elementary row operation and I get B. Suppose I have two matrices A and B and a succession of elementary row operations such that when I apply this succession of elementary row operations on A, I get the matrix B, then we say A is row equivalent to B, and symbolically we write this as, and symbolically we write A row equivalent to B. Now, observe the following. Suppose A is row equivalent to B, what do we mean? We can move step by step from A applying one elementary row operation at each step to finally reach the goal B. Now, each step is an elementary row operation, and we have seen that each elementary row operation is invertible, and therefore, we can reverse each step and then we can go back from B to A purely by a sequence of elementary row operations. So, we will now apply all these together and observe the following properties. One, we can go from A to A by one step, namely simply multiply the first row by 1. So, we can go from A to B by one elementary row operation. So, A is row equivalent to A itself, A is row equivalent to itself, because we can go from A to A by a finite number of successive elementary operations. We call this property the reflexivity property of row equivalence. Secondly, as we have observed, if I can go from A to B by elementary row operations, and since each elementary row operation is reversible, we can also go from B to A by elementary row operations. So, since each ERO is invertible and again an ERO, the inverse is again an ERO, we see that A will be row equivalent to B if and only if B is row equivalent to A. If I can go from A to B, by retracing the paths I can go from B to A and vice versa. So, A is row equivalent to B if and only if B is row equivalent to. This is called the symmetry property of row equivalence. The third property is, suppose A is row equivalent to B and B is row equivalent to C. What does that mean? That means I can apply a number of steps to get to B, and this is a finite number of elementary row operations, and maybe I can apply, let us call it as K, F1, F2, Fs to go from B to C. The A to B there are a finite number of elementary row operations, B to C there are a finite number of elementary operations. That means I can go from A to C by a finite number of EROs. Why? First apply all these E1, E2, EKs, then apply F1, F2, Fs, you will go from A to B and then to C. So, you will go all the way from A to C. So, that means since I can go from A to C by a finite number of EROs, it follows that A will be row equivalent to C. So, the conclusion is, if A is row equivalent to B and B is row equivalent to C, then A is row equivalent to C. This is called the transitivity property of the row equivalence. If any relation has these three properties of reflexivity, symmetry and transitivity, it is called an equivalence relation, and hence row equivalence is an equivalence relation on the collection of all m by n matrices. Now, suppose A is row equivalent to B. Now, we get back to our basic problem of the homogeneous system of equations. Look at the system corresponding to A x and look at the system corresponding to B, the matrix B, Bx equal to theta m. Now, how do I go from A to B? I go from A to B step by step by elementary row operations, and we have observed that the elementary row operations do not alter the set of solutions of the homogeneous system, and therefore, at each step the system possesses the same solutions, and therefore, at the end A and B, the corresponding homogeneous system will possess the same solutions. Since EROs do not alter the set of solutions of the homogeneous system, we see that the two systems have same set of solutions. Therefore, conclusion, A is rho equivalent to B implies the systems, when we say systems we mean the homogeneous systems Ax equal to theta m and Bx equal to theta m have the same set of solutions. How do we exploit this? The idea is start from A, apply suitable EROs step by step to A to get a row equivalent matrix B, then we can solve Bx equal to theta m instead of Ax equal to theta m, because both have same set of solution. The idea is choose EROs so that easy to solve Bx equal to theta. How do we do this? We shall see this in the next lecture.